Okay, so while we wait for 1 minute before we start, for those of you in pain, I remind you that on the board there are micro instructions to access a YouTube channel where the class is actually being streamed. It's public, so you just look for search for CBMM on YouTube, and you should see me jumping around. Some of you noticed we accumulated a certain amount of typos and mistakes and violations in the psets date. Not a lot actually. It's minor, but we're going to fix it. So there's going to be an update on the website, and I circulate an email.
And thanks to people who told us.
And thanks to people that told us. Mailing list. You should be able to access Stellar and register yourself. According to our records, we have something like 220 people. So it looks like you managed to register. We're saying now these people should not be all people taking class for credits, but still have something like 150 for credits. So it's going to be crowded. Any important communication from the TAs, instructors? All right, so we'll get started with the actual content of the class. I'm Lorenzo. I'm going to be teaching you for the next month or so. I'm going to essentially, today is kind of a warm-up. We're going to introduce the main ideas in machine learning in the context of statistical learning theory. But really, I'm not going to tell you a lot about theory. Today I'm mostly going to tell you about the setting. Okay? What I mean by the setting is the set of ingredients that set up the problem for us. Okay? The nice thing about what we're going to do is that we're going to focus on supervised learning, which is by far the branch of machine learning that is more mature and developed and understood. And the definition of a supervised learning problem is extremely short. Okay, so we're going to start from that. It's just 2 lines, okay? But there are 2 pretty dense lines, and so we're going to spend a bit of time unpacking each one of the symbols in these 2 lines. A lot of these things will be mostly familiar to you if you didn't lie and you actually took a machine learning class before. Still, even if you took a machine learning class before, it should be a fresh review of some ideas, perhaps put in a kind of slightly more mature perspective. And then in the last part, we're going to discuss a bit some ideas related to what does it mean to solve a learning problem from a mathematical point of view, to which extent we can make an assessment on how well a learning problem will work on the future. This is really like a sprinkle, a teeny tiny appetizer. I'm really not going to tell you anything about this. We're just going to build a bunch of algorithms for the next month or so. And then when Sasha takes the stage, he'll go back exactly to this 1 line, telling you how the algorithm we have introduced in the meantime can be somewhat studied within this machine learning framework. So, the 2 things we want to do are introduce the problem setting and then discuss a bit what do we mean, say, by generalization, or what do we mean by, in which sense we can say that a solution works. Okay, generalization here is broadly intended as a word that refers to the idea that based on data today, we can actually make some prediction and take action in the future. Okay, we're going to be more precise in a minute. Okay, it doesn't work. So, as I told you, one nice thing of supervised learning is that we can actually, it's basically a definition that is really like just 2 lines, okay? We're going to assume that we have a pair of spaces, okay, with a probability distribution. X is the input, Y is the output, and P is the distribution over X and Y, okay? We're going to assume also that there is a loss function. Okay, and the loss function takes a real number and an element of the output space and returns a positive number. Okay, it's the cost. We'll see that we're gonna see it as a function that somewhat measures the cost we pay by making a prediction. These are really the only two ingredients we need to define the problem, and then the problem we're gonna cast as a minimization problem. And the problem is to minimize the following function. Sorry. I have we updated a bit the notation, so I might have a couple of glitches here and there. Okay, so you have to minimize the expected loss function. Here the expectation is taken over all possible pair x and y drawn with respect to the distribution p. The point is that we're not given p, but we're given a bunch of input-output pairs sampled according to p to the n. Okay, I intentionally write this definition in the shortest, less friendly way because we're going to spend an hour somewhat unpacking all the symbol here. But this is just to show you how you can make it precise and self-contained, and in just 3 lines introduce the problem. Why do we call it a learning problem? Essentially because of this thing here. You want to minimize a function that represents error that you can interpret as the error on all possible data, past and future data, but you don't have access to this directly. Okay? All you have is a bunch of data, finitely many, and here is finite, that you observed from the distribution. Okay? So it will not be possible to solve this problem exactly. We'll have, that's what we're going to discuss when we discuss generalization. We have to set up for a notion of approximate solution because it's in general not possible to solve this problem exactly. We are going to, based on data, we're going to generate a candidate solution, okay, an estimator of the solution, and then we're going to ask ourselves, what does it mean to solve the problem? In which sense we can quantify how far is what we can produce based on data from the best possible function. So far, so good? So P is not known, L is available, okay? And it's part of the definition of the problem. Maybe a word about this. What does it mean here? I'm being a bit vague about what does it mean. Essentially it means all the possible functions for which this expectation makes sense, okay? We're not going to dwell into the details of what this means. Essentially just minor integrability, measurability condition works fine, okay? So just view this as all possible functions, okay? For which that makes sense. All right. So what do we want to do now? We basically, as I told you, want to just go in and somewhat look at each of the elements that define the problem and take a bit of a look and see what we mean by those symbols. Okay, many of you already have an interpretation of those symbols, have some experience. Let's just get back to it. Okay, so the very first thing is the input and output spaces. X and Y. Okay. What is the classic example of input space you have in your mind?
Numerical.
What?
Some numerical data.
So numerical?
Data.
Yeah, like what?
Vector.
Vector space. I mean, I think the classical example is RD. Okay, this is going to be the running example in most of the class. Okay. RD is the prototype example. We often think of, I think we're going to use small d here. We're going to think a d of being potentially large. Okay, if you look at classical statistics, which is going to deal with problem very similar to that, oftentimes d was say 1, 2, 3, 4, 5. For us, d can go in the order of thousands, tens of thousands, even up to millions. Okay, so it's going to be potentially very high dimensional. But the list of examples here is very long, okay? And if you try to make sense of all the possible list of examples you can make, perhaps one distinction is among spaces having one special features or not, okay? You can take RD, you can take the space of matrices, you can take the space of functions, operators. You can be pretty fancy, you know, this is fancy, but for example, if you take function, this is what is called functional regression. You have signals, you measure signals in your input, and you want to just distinguish in a certain kind of signals or not, okay? So it's not so crazy. What have all these spaces in common? If you take this set of objects, they're very different objects, right? But what do they have in common? If you take any of those two objects and you add them up, you obtain yet another of those objects. If you take two vectors and you add them up, you obtain a vector, two function a function, two matrices a matrix, and you keep on going. And if you multiply any of those two vectors by a number, you still get one of those guys. In other words, these are vector spaces, okay? Despite the fact that, of course, these are in our, you know, they're typically much more complicated objects. So matrix is an operator and function are more complicated than vector. In some sense, we can think of them as vector. We can manipulate them as vector. And that's nice. Because, for example, if you want to compare any of those two objects, we can just take the difference and take the norm. Okay? That's for free, just because it's a vector space. So being a linear space, or a vector space. Again, it means that you have these two axioms. You can add things and multiply them by number. It's a nice feature that sets somewhat a bunch of problems apart. What about the rest? Well, first of all, what's the rest? Can you give me an example of a space of object which is not a vector space?
Feature space where the values are binary.
For example, binary, okay? Binary values. Okay, more generally binary strings. Okay, if you just take strings, more generally strings, not even binary. Just give me an alphabet, and I build strings from the alphabet. Okay, so strings. What else? Graphs. What else?
Trees. Trees.
Trees. No, it's graphs. It's too close. I'm too lazy. I have too much stuff to cover. These are all discrete. Can somebody name a continuous, you know, something more like function, something that is more of a continuous structure? Manifolds. Okay. Manifolds say the space of curves. They have curves. Okay, embedded in some high-dimensional space. For example, you know, you work in shapes. You know, you do graphics and you have to distinguish shapes or contour. Okay, things like that. They're not graphs. They're not. Of course, you're going to discretize at some point, but you like to think of continuous objects. So the thing that all these have in common is that these guys do not have a linear structure, and this typically makes life harder. Okay. Fair enough. This is one distinction which is useful just to put somewhere in your thoughts. What about the Y's? Well, the story kind of repeats. The interesting bit is that while the fact that you have this different structure in the input doesn't really have a name, when you move to the output space, whichever output space you choose is going to give rise to a new problem with a different name. Okay? For example, if you take R, or more generally RT, as the output space, well, actually, no, we need to be slower because we really want to give different names. So if you take R, we're going to call this regression. If you take this RT, we're going to call this multivariate regression. But sometimes you will also call this multitask learning. You just view this as a problem where each output has an interpretation as a different task. Okay. And then you can keep on going. You know, if you have matrices, this is called matrix valued learning. These names are not so interesting. Okay, so you can keep on going. I'm not going to repeat. The list is just the same. Then you can go to a space of, let me call this structured object. So you can, similar to here, you can go to the space of structured objects. Now the name structure object is funny if you think about it. This is typically a running name that is used in machine learning. It's actually a funny name because from a mathematical point of view, they have less structure. They lack the vector space structure and all the things that come for free. So they lack the inner product structure, the norm, the distance. They don't have it for free. But they're called structured object because typically this thing corresponds to some interesting semantically interesting object in a rough sense. Again, say a sentence, okay, a speech recording, or a network or something that has much richer structure from whatever intuitive perspective, okay? But from a mathematical point of view, it's just something that you cannot even multiply by a number, and it's gonna make your life harder. As a matter of fact, if you look at what we really know how to do, is basically this stuff, okay? R, D, and R, okay? And a little more you'll see in a minute when you do classification. But the rest, yeah, it's something that is ongoing. Yeah?
In the case where y is r to the t, we need to change our problem formulation so that f has code.
Yeah. Yeah, so this is always a choice. So this problem formulation here is mostly for the case where we're going to do regression, okay? Generally, so I'm thinking of this because it's going to be a primary example, mostly for the case of regression. You can consider here the case where you put here y, or more generally some other space g, okay? So let's this definition I'm intentionally considering this case because this is a bit of degrees of freedom that makes your life a little complicated, okay? You know, for example, when you do classification, we're going to see in a minute that your output is plus or minus 1, okay? But you actually try to estimate real valued functions, okay? So that definition reflect to that, but that's a very good point, okay? That's an intentional simplification of the setting. If you don't like that, just think replace R with some other space which has a linear structure. Okay? Other questions? Okay, look, what is the main example here? Well, we studied strings. We started from binary strings. The case where the output is, say, 0, 1, or plus minus 1, that's probably the most common example, and that's what you call binary classification. The case where you have a set of binary, a set of symbols from 1 to t, or ABC, whatever you want to call them, is multi-class classification. But then we can keep on going. Okay, here you have multi-label. Okay, you have that each object can be assigned more than one symbol, and you can keep on going. The list is extremely long, and you can take the case where, for example, the output is a manifold, is a graph, is a string. Okay, these are all potential cases. All right, fair enough. This is the main. I think this point of having or not the linear structure is what we're going to play some role in our discussion and when we try to extend things. And it's basically what put aside the classical machine learning from what is sometimes called structured input or structured output machine learning. Okay. So the other quantity that appears right from the beginning is the data distribution. Okay, this is a huge conceptual importance because all of a sudden we sneak in probability into the picture. Okay, and it's a very reasonable question. Why do we do this? What we're trying to achieve? What we should think about? Okay, so. So importantly, we're going to always make minimal assumptions that ensure that this distribution can be split. In a distribution over the inputs and a distribution over output. A marginal distribution over the input and a conditional distribution of the output for each given input. Okay? We're going to just wonder a bit, how well shall we think about this, okay? So, as far as the output distribution is concerned, we often think about that as some form of noise, okay? It's about telling you when you give me an x, I cannot tell you exactly all the time what is the exact output, but there will be a distribution of potential answers, okay? We have to live with that. One common way to think about this is to assume in regression what is called the regression model, okay? So, in regression, a regression model, the simplest one, well, not the simplest, but most basic one is assuming that yi is given by some fixed function f star, unknown, okay, you don't have it. And then you corrupt this with some form of noise. Okay, so epsilon I, for example, could be Gaussian random variable, okay, just a normal standard Gaussian with variance sigma. Okay, sigma is the noise level. Okay. So in this case, literally you can think as essentially thinking about P of y given x is exactly the same as thinking a distribution of the noise. What is the distribution of yi if epsilon I is under Gaussian? Gaussian where you just shift the mean, okay? So basically you're saying the values of y are all gonna be around f star, or they're gonna somewhat centered. And of course, nobody told us that we have to just do Gaussian. You can take Poisson, you can do asymmetric, you can do crazy noise model. But the important bit is that the moment you fix a distribution here, then yi is going to inherit for each x a distribution, which is exactly the one we're talking about here. Okay? So this is the main running case for thinking about the role of the conditional distribution. This is really the case for regression. What about binary classification? Well, does this make sense for binary classification? Not really clear, right? You can make some other models. We're not going to delve into this too much. But we're going to just observe that P of y given x in classification all reduces to just not a distribution, but a point mass distribution. So not a general distribution, but a point mass distribution with just two values. P of 1 given x, P of minus 1 given x. Now, in which sense this corresponds to some form of indeterminacy or some form of uncertainty about the value of our classification problem, where the simplest case is, for example, if you assume these two guys to be bell-shaped, possibly Gaussian, but possibly not. And essentially what you have is that in some sense the fact that they have an overlap, that they have somewhat they're not disjunct, is somewhat a measure of the fact that they have some form of noise. Okay, there is regions where I'm not 100% sure that I can make a prediction confidently because, or maybe we have to agree with confidently. We cannot make it with confidence 100% because I have some confusion zone. Okay, and I'm not going to skip the equation. You find them in this supporting material that I think it's already online. Actually, you should be able to go on the website and see the slides that corresponds to this. But it's very easy to see how you can define a notion of a real number that essentially giving you the area under this curve, okay, or how much stuff there is in the overlap between these two curves. And so this is yet another way to see why the P of y given x somewhat control the noise in the problem in the case of classification. Okay. So far so good. So what about the marginal distribution? Okay, what about this P of x? Why do we put a marginal distribution? Why there is the distribution on the input? Why don't we just assume that it's a fixed uniform? Yeah.
About the noise.
Yeah.
Is there a reason why I use 1/2 as a reference in the lecture notes?
Say it
We are
again.
defining the delta sigma. The definition is x belongs to x given p 1 given x. The class is 1 minus 1/2. It's more than
Eh? Oh, you mean for classification?
yeah.
No, I mean I skipped that. So let me take that offline. I skipped that because I want to make it simple. This is just essentially it's a way to say essentially if what I wrote in the notes is that if P of 1 given x, if there are a lot of x's for which P of 1 of given x is close to 1/2, it means that there are a lot of situations where that this area is very large in some sense. There is a lot of overlap. There is a lot of points where P of 1 given, they have to sum up to 1, right? So if P of 1 given x is close to 1/2, P of minus 1 given x is also going to be close to 1/2, and it means that it's an area where there is a lot of confusion. Okay, that's the basic idea. That's what I wrote in the notes. But again, I skipped it here because at this level of discussion, it's not super important. Okay, it might be that at some point Sasha is going to discuss things where you want to quantify this intuition, and then you need exactly that equation. Introduce what is called a noise condition, and you can show that it actually helps to quantify how hard or not is a problem from a mathematical point of view. But for now, I just want to give you a more high-level view on why the P of y given x contains information about noise in both classification and regression. Okay. was the question or just?
Oh, no, but so you asked like why we don't assume it's uniform. It seems to me that lots of real world situations we don't have a uniform distribution. Maybe it's impossible. Like if it's over
But why do you even assume that there is a distribution? Okay, why don't you just assume, for example, that your data are just fixed? Okay, what do you want to achieve with that? What kind of information there is? If you like the word uncertainty, you can say that there is uncertainty, that the P of X, describes some form of uncertainty. What things can be hidden in that uncertainty? You can think of many things. If you think from an engineering perspective where you go and sample your domain, there might be a situation where you don't have full control in the way you sample the domain. There are some noise in the sampling process. Okay, I want to sample here, but maybe I'm going to sample a bit further away. There might be a region of the space which are intrinsically harder to sample. Okay, so I have less sample from some regions. It might be that the number I get of my samplings get quantized or corrupted in various ways. Okay, so I'm supposed to measure, a certain number of features, measurements, and get a set of numbers, but I don't get those because they get corrupted or I quantize them. Okay, it's all hidden in there. It's all hidden in this distribution. Make sense? Okay, so as you say, a lot of real-world problems probably don't have a uniform distribution, but it's more than that. We are somewhat dumping there a lot of elements that we could possibly try to model more specifically, but as you'll see, a feature of what we're going to discuss is try to develop things in a generality. Okay, we're going to just try to identify some elements that seem to be important, and then try not to model every single element of the learning process. For example, there could be a lot of things hidden in P of X, but for us, it's all there, and we just take that as a given quantity that hides everything inside, and we want to know how far we can go without making any further modeling of P of X. As here, we don't actually going to make this specific assumption or example. We just want to know how far we can go for any distribution P of Y given X. Okay? One thing to keep in mind is that this distribution also hides somewhat the fact that data can be potentially extremely high dimensional. Okay, if you're in the case where X is RD, if this was a uniform distribution, it means that we can take data from all over this high dimensional space. Okay, and it's very hard to imagine we'll be able to learn in an input space which is say 10,000 dimensional with a lot of information just to explore the space intuitively. So an assumption that is often made is that even though X could be equal to some very high dimensional space, say D or the 10 to the 6, our data, they don't really live in this big space. Okay. The first observation you can do is, again, the case of images is the obvious one. Take an image which is 20 by 20 or 200 by 200, and then take any vector which is 200 by 200. Okay? Suppose that you take the space of faces. The space of faces is going to live in this very high dimensional space, 200 by 200, but it's not by no means is going to occupy the whole thing. As a counterexample, just think of just shooting 200 by 200 random numbers. It's not going to be a face. Okay? Probably it's going to be pretty far away. So if you think of this very high dimensional space, already you can think that probably the data don't occupy the whole thing. They're going to occupy some portion of it. Okay? That's one first observation that is good to put in mind. The other thing is that for many, many data, that blob has actually some nice structure. Okay? Maybe not exactly, but it's close to have some nice structure. The nice thing they like people to think about is things like symmetries. If you look at my face frontally, you have that this pixel and this pixel are probably very much related. Okay, and in fact, all these pixels, it's a contour. So all these pixels here probably have a very similar, well, not similar, but a very related behavior. And once you know half of my face, given my asymmetries, you can probably predict decently well the other half. Which means that is not just a set; it's a set with a lot of structure. Okay, and when we try to make things mathematically nice, we like to think of this as a manifold, okay, which roughly speaking is a curve. I make a circle there because I'm aware of my drawing limitations, but you can think more generally of that as a surface or some kind of nice curve, okay? And most likely that's a wrong assumption, okay? There's no reason to believe that things are going to be nicely lying on top of the manifold, but you can think that gives some hint of what might happen in the real world. So people like to think data is lying on a manifold or close to a manifold or some kind of structure or even much more abstract definition. But I think to keep in mind is that the high dimensionality, part of the high dimensionality we're going to take care by assuming that somewhat the distribution of the input is not just living in the full high dimensional space. We're just going to take samples that somewhat lie in some structured subset of the input space. Okay? Okie doke. Check. The first line is gone. Okay, we have it. What about the second line? Well, again, so the loss function, okay, is going to be this thing here. Let's make an example. What is an example of a loss function? Least squares, which means the square loss, which is y minus f of x squared. Okay? If I have to draw it, it's convenient to give a name to this guy. Let's call it alpha. Okay? Because at this point, if I put alpha here, again, bear with me as I draw, this is what we get. Another example? So when do you use this? Do you use this for regression or classification? And that's wrong. You should use it for classification, but we get to that later. But let's say that this is just for regression, okay? Then let's make a couple more examples of regression before we move to cross entropy, which is typically used for classification. Other examples?
Absolute value.
Absolute values. This becomes harder. Look at this. Boom. Boom. What else? A what? You can take LP norms, okay? You can just put a P there, okay? If this class was taken when me and Sasha had shorts, you would have discussed the epsilon insensitive loss function introduced by Vapnik as a way to do some form of robust loss function. Essentially, I'm not going to write the equation because it's just annoying, but it's essentially a loss function which is flat around 0 and then goes up linearly. So it's kind of an absolute value that you flatten around the origin. So if you look at what is a super vector machine for regression, it's basically the one thing that uses this loss function. Okay. Perhaps one thing to observe is in all these cases, the important quantity, the argument is not just any pairs y and r. It's actually the difference between y and r. Okay. The important quantity in regression is the difference. What about classification? Okay. Binary classification. Okay, cross entropy is the fancy example, but what is the baby example? If you make a mistake, you count. If you don't make a mistake, you count 0. Okay. Okay, how do you want to write this? You can write it like this. You basically say, I'm going to take the product of f of x and y. If they have the same sign, I'm going to pay 0. So I made a mistake. If you have the same sign, I'm going to pay 0. But if they have the wrong sign, you know, I'm positive, she's negative, the other way around, then I'm going to pay 1. What is the shape of that and how do I draw it? What is the important quantity here? If I want to draw in just one dimension, how can I draw this loss function? Does it depend on the difference? What does it depend on? Depends on the? How do I combine y and f of x to obtain one number? I don't take their difference, but by inspecting the board, I can see that I take their product. Okay? The product is what matters. Okay? Just tell me, do they agree or not? So I can actually draw this by doing this. So if I put here y of x, when it's negative, I pay 1. Okay. Do you like the loss function? Do you like that one or the one above better? Is there something that you don't like in that loss function? It's a little bit not differentiable and quite a lot non-convex. Okay? So if you actually try to optimize that, no matter how much back propagation you throw at it, you might have a hard time. So it turns out that what you try to do in practice is that you can try to replace that with what calls oftentimes a surrogate. What is a surrogate is something else that looks a little bit like that. It's actually an upper bound, but it's much nicer. Okay? If you draw it as a curve, it's nicer. For example, one thing you can do is that you can consider the following: the logarithm of 1 plus e to the y f of x. How does this look like? It looks like this. So it stays, as you can see from my bad drawing, it always stays above. Okay, it doesn't enter there, and it converges to 0 on this side. So this, I'm not sure, you can view it right away if you've never seen it before, but the idea is that in some sense this logarithm and this e somewhat cancel out in this regime. It becomes linear, and then you have this decay. So in some sense, it's a clear upper bound. This one is it differentiable or not? And is it convex or not? So life is good, okay? And you can call it G-stick, or you can just call it cross entropy for binary classification if you prefer. You can manipulate them a little bit and show that they're just the same. Okay, fair enough. This is one possible choice. Another possible choice is this one. Again, this stuff should not happen, okay? This is a tangent to this. You go straight into 1, and then you become flat. I'm going to write it here. So when you write this modulus with a plus, this means that you're taking the maximum between 0 and alpha. So if alpha is positive, you let it go. If it's negative or 0, you clip it to 0. Okay? So this is basically what you get. You get something which is, you see here, I get the same thing, but I shifted by 1. So now I get something which is flat up to here, then it starts to go up, and then it passes right through this kink, and it keeps on going. So again, it's an upper bound. Again, it's clearly convex. Is it differentiable? Not really. There is this one point where you have this guy and this guy. It's okay. We'll see that left and right derivatives are going to be enough to deal with this kind of stuff. Okay. What about the square loss? Can I draw it in this picture? How does it look like? Well, to draw it in this picture, I would like to rewrite this one equation as something that depends only on the product. Can I do that? Yeah, I need to write, instead of y minus f of x squared, I need to write something that depends on y times f of x, because otherwise I don't know how to write it there. How do you do that? Well, it turns out that if this is just plus and minus 1, then you can also rewrite this as 1 minus y f of x squared. Okay? You can do this in 15 different ways. Okay? You can just factorize out the y. Of course, it matters that y is just plus or minus 1. That's exactly what you're using here. Which means that the square loss function looks like this, which is kind of funny because it's still an upper bound, it's still differentiable, it's still convex, but you pay on the right-hand side, which is the reason why at first sight this looks like a bad choice. Okay? I'll see in a minute that you can view things from a slightly different perspective that somewhat rebalance out the intuition. Fair enough, these are the main loss functions in regression classification, I would argue. What about loss functions for all the other spaces we described? We said there are many, many potential choices. What are the loss functions used there? Well, the long story short is that there is no such list. Okay? Essentially, if you take things like even just, multivariate regression, you can just take all these distance-based loss function, and that's fine. So if your output is RT, you can just replace the square with the norm, and that's okay. But for everything else, it's kind of complicated. Even for multi-class classification, there is quite a bunch of relatively recent papers that somewhat try to figure out what is the best way to define a loss function. If you look at some more exotic choices, say strings, graphs, manifolds, then all bets are loose. Okay, there is no, building good loss function from an algorithmic point of view is a challenge. What we'll see that to some extent, I think you're going to appreciate this when you see the statistical part that Sasha is going to describe. If you want to just do statistical analysis, in many cases you can work in very general scenarios, just making very minimal assumption. When you have to do things in practice, you have to come up with actual choices. And if your output and input are not the usual easy choices, i.i.d. essentially, things become complicated. Structural prediction is an interesting field, essentially because you have to come up with good ways to represent function and measure errors when you make predictions. Okay, that's why I don't even make one example. Okay, because it's just case-based. Every problem comes with its own loss function. Okay. Okay. Any questions or comments? As you see, the choice of the loss function is extremely important because it appears right here. It appears right and is one of the two main ingredients of the problem. Okay, it defines the problem completely. When you can appreciate this fact even more, we start to take a look at the expected risk. So let me we're going to denote this quantity by L of F. Okay, is the expected loss, it's called the expected loss or the risk or the expected error. The different name is all the same thing. It's the expectation of the loss over a possible point. When taking a bit of a look at that, we can get some further insight on the structure of the problem. Particularly, one thing you can ask is, let's play theoretician for a minute, and let's pretend that we actually have access to the full distribution, and let's try to see what is the impact of the choice of the loss function on the problem. Okay, how impactful is the choice of the loss function? To do that, the thing we might try to do is to look at what you might call the target function. Okay. I don't know if it's an official better name than this. I'm gonna just use this name. So this target function is fp, and this is the argmin. Argmin, you know what it means? Just the minimizer rather than the minimum. It's the place where you achieve. And here I just put the dependence on P, the distribution, just to remind that this is a theoretical object you don't have access to, but clearly this is also going to depend on L, the loss function, okay? Now you can ask yourself, well, can I see what that is, assuming for a minute that I have access to the distribution? Can I just manipulate the expression a little bit and see what is the corresponding quantity? Well, it turns out that here, if you actually split I'm going to make 3 gazillions typos during this lecture, so the more you point out while I speak, the more you can save yourself pain at home. A standard way to understand the behavior of this, the complication of this is that if you try to somewhat do your usual calculus on it, you have to deal with functions rather than numbers. We like to take derivatives with respect to numbers, right? So there is a trick that you can do under pretty general assumption, which is take the conditional expectation of this thing, okay? Just take the expectation of x first and then the expectation with respect to y given x. Because now, rather than optimizing the whole thing, you just optimize the inner integrand, the one that depends on x. This just become a number, okay? Just become a value, is f of x. It's like saying, can you find the best function f? And I tell you, yeah, I'm gonna find the best function of f at x, then at x1, and at any x, okay? That's the trick. Of course, there is some regularity that has to be satisfied for this to make sense, but it turns out that it's very minimal. So that's what you're going to do. So the nice thing about this is that once you do this, okay, then you can make the calculation very explicit. For example, let's consider the square loss. In this case, and we're going to skip the calculation, essentially you just get the square, you derive, okay? The squares goes away, it all becomes linear, and it turns out that what you have is that the f of p can be actually write explicitly and it is just the conditional expectation of y given x. Okay? What does it mean? You take each point. For each point, you don't have only one output. You have a distribution of output. The best thing you could do in heaven is, average them out for every point. That's what this is. And this is called the regression function. What if I choose another loss function? Do I still get this regression function as my target? What do you think? Is the question clear? The question is, here I skip the calculation that goes from minimizing this with respect to fx in the case of square loss and finally that you just get this expression. So what if I put here the absolute loss? So I replace the square with an absolute value. What you get?
Median.
You get the median, okay? So we just want to stop 1 second here to realize that it means that the loss function changes where we're going to, okay? If you're choosing loss function in practice, this is not typically how you think about it. You often look at computational consideration, logistic versus SVM, things that are completely, in another part of your brain. But if you take from a statistical decision theoretic point of view, a statistical theoretical point of view, this is what's going on. As you choose the loss function, in regression, you're shifting your targets to different places. In one case, you're shooting for the average. In the other case, you're shooting for the median of the distribution. And so every time you come up with a loss function, you can ask yourself, what am I shooting at? Okay? What is this corresponding? Because that's often the way you do it. You build the loss function for other reasons, then you can ask yourself, okay, how do they change the problem? Where am I going? Of course, there's nothing special to regression. You can play the same game for classification, okay? These are what's happening for regression. In classification, the situation is a bit more interesting. For example, you can consider this guy. Again, I told you this guy is a mess to optimize in practice, but in theory, you can just do this, okay? Just a tiny modulation. And this would be the best possible function in classification. Anybody know what that is?
The majority, where it would have the same sign as whichever one is more probable, plus or minus.
Right, so basically, if you have access to the probability, you can take a look at the probability, conditional probability at every point, and you see which one is bigger, okay? You can take basically P of 1 given x, P of minus 1 given x, okay? And for example, you can take the sign of this expression. This means I'm going to check P of 1, and if it's bigger, I'm going to say 1. If it's smaller, I'm going to say minus 1. This is called the Bayes rule for classification. And of course, if you think about it just 3 seconds, you realize that you can write that thing in 4 different ways. Okay? Fair enough. Okay? But we don't. Here you see how the loss function, for example, is something that enters the picture because you don't know how to optimize things based on this kind of loss function. So what do you do in practice? Well, in practice, you replace that with some surrogate. Okay? And I just showed you a second ago that the square loss, albeit weird, it is a surrogate. It's a convex, differentiable upper bound on that quantity. How does this big expression look like in the case of classification? It's the expectation over all possible y's, okay? But how many y's do you have in classification? 2, okay? You have 1 and you have minus 1. 1 is probability of 1 given x, minus 1 is probability. So this is the same as P of 1. Give myself some space. Okay, do you see that? It's just 1 times its probability, which is P of 1 minus x, and then minus 1 times its probability, which is fp of minus 1 given x. Is that okay? All right, so now if I show you this one equation, would you want to use the square loss for classification, yes or no? Does it make any sense, or is it just completely nonsense? This seems to be a common answer. Why not? I mean, below I'm shooting for the sign, above I'm not shooting for the sign, which means that I have to take the sign, which also makes a lot of sense, because what you all of a sudden it makes sense. The thing that we do in practice of taking the sign, it basically comes out of a calculation, analytic calculation. Okay. So from this perspective, one should expect the square loss not to do something insane. Now we can see if it's the best thing or not, and it turns out that no, it's not the best thing, at least in theory. In practice, you might want to try, but from this perspective, it's fine. Okay, but we mentioned a few other choices. Okay, for example, the logistic loss function. Okay, can we compute the FP, the target function for the logistic loss function? You do exactly the same kind of reasoning, and it's easy to see that in the case of logistic, what you get is that FP logistic, don't make me write cross entropy because it's too long, but it's the same thing. This one you might want to check on me because I haven't looked it up, but I think that's the expression. Basically, something depends on the ratio. Again, this is easy to check. Again, what you have is that is something that depends on the ratio is going to determine the sign of the logarithm. And again, you take the sign and you get back the best possible thing. A bit of an interesting. See this? This is weird. A bit of an interesting fact, which at least I discovered after factor. This is not the way I learn about SVMs. Is that if you take this loss function, which is linear and then flat, the hinge loss function, it has somewhat a magical property. Okay, its target is the Bayes rule without the sign. Even though you allow yourself to take, in principle, function with real values, the hinge loss, if you have infinite power, which of course might be a bit of a strong assumption, it actually lands on the right quantity. So this is an interesting thing, that if you actually consider the hinge loss, FP is the Bayes rule. It's really the Bayes rule. So here, FP is not the Bayes rule. You have to take the sign to get the Bayes rule. Here is exactly the Bayes rule. So the hinge loss, in some sense, is naturally tailored for classification because its target is exactly the target of classification. You don't even have to take the sign in principle. In practice, you will have to do it. But in theory, that's really shooting for the right thing. And you can quantify even more. You can take more refined way to look at classification versus regression. And what you basically see is that, in some sense, the hinge loss seems to be, from a statistical point of view, the minimal relaxation to the classification problem. And I'm not being precise here. So in some sense, you have this step and you want to make it convex. And in some sense, the hinge loss is the minimal way in which you can do it. The logistic is a bit further up. And the square loss is a much more dramatic way of finding a convex relaxation. Okay? Yet again, they all make sense, and you can all use them in practice. What we want to get out of this is, in regression, by choosing the loss function, you're choosing the target of the problem. In classification, by choosing a loss, you're deciding in which way you want to relax the problem. Okay? And how you proceed from here often depends a bit on what's your final goal and how much time you have to spend and what kind of computation you're willing to perform, because as we'll see, the choice of the loss function gives rise to algorithms with different names. Okay? Least squares, or Tommy like to call it, least square supervector machines is the choice of least squares. Just kidding. The least squares is an algorithm from Gauss from the 1800s, but somebody decided to call it least square supervector machine in 1990. So, logistic regression is the algorithm corresponding to the choice of the logistic loss function, hinge loss, SVM, and so on and so forth. You really, depending on the loss, you find different names of different algorithms. Okay, so we actually went almost to the end, because now we have, how much time we have? A little bit. Okay, so we We know that there are different choices of input and output, that the framework is very general. We know that the input, what set apart different input and output is the fact that they have, from a mathematical point of view, a vector structure or not. Vector doesn't mean that they're vectors, but just that you can sum them up. So matrices are fine, operators are fine, functions are fine. If you take string, graph, manifold, these are different things. Okay. The probability is somewhat the place where we somewhat dump all our ignorance and uncertainty about the problem. Okay. So noise, quantization, sampling, it's all hidden in either the marginal or the conditional distribution, and we want whatever we do to be somewhat robust to that. The loss function is somewhat the way we measure the error we pay when we say f of x, when we should have really said y, and it's of course something that is needed because we're going to typically look for a deterministic rule to predict within a stochastic environment, so we're going to make mistakes. Okay. There is no such thing as the perfect rule, and yet I'm going to look for a deterministic rule. So of course I have to pay a mistake. The choice of the loss function is somewhat part of the definition of the problem. It's somewhat something that we know how to do for cases where we have a linear structure in the input, in the output space, but it becomes a challenge when you lack a linear structure, manifold valued learning, graph valued learning, string valued learning. It's something that is more of a challenge. And what you can see is that if you take a closer look at the expected risk, by choosing different loss function, you're choosing different target for your learning procedure. What I mean by target here is literally that if you're given more and more example, you're going to go in different places. Okay? And so that's basically what we have done so far. I snaked in this last one line with this super heavy notation. But this basically means the following, and it's super important, and it's going to be the basics of a lot of our future theoretical reasoning. Okay, let me actually explain the notation first. The notation just says, okay, you view this as pairs, okay, all sample from the same distribution product, okay, which means that it's always the same, and then I just take independent samples, okay. So this is what you sometimes call the i.i.d assumption. Identical independent distributed, okay? Always coming from the same P, and they are independent to each other. So each new sample brings in completely fresh information about the process. Now, this is going to be a super important assumption. I'm sure Sasha is going to comment on it extensively. The basic idea you want to think about is underlying anything we're going to do is going to be some form of large numbers, okay? And it's going to be extremely important that we have a distribution, a reference distribution. So every time you toss a coin, you're hoping that you can understand if the coin is fair or not, because it's always the same coin. You don't change it. Its distribution is always the same. So every time you observe something, you accumulate evidence towards understanding what is the final distribution. If the distribution itself is changing, then you enter a much more complicated situation. Okay? So for us, in most of our reasoning, the idea of having a fixed distribution is going to be somewhat conceptually important. That's where we want to learn something that is there, and we just observe it. And the more we observe it, then the more we can learn about it. Independence is going to play less of a crucial role. I think technically we're typically going to use it, but many of the things we're going to say could be perhaps extended with not much effort. At least in my view, the fact that we make the identical distribution in this learning setting somewhat a bigger role. I think perhaps when you discuss online, you're going to comment on this kind of stuff. Anyway, so we're going to make this assumption as part of the problem, at least for now. Yeah, go ahead.
F of x on the y.
You don't want them symmetric?
The definition of L is not symmetric.
So you want them like this or like that? Because I like to change every 2 lines. I don't care. All the loss function I know are symmetric. So. Yeah, this way we don't, I don't know if I know loss functions that are not symmetric, but now you can make them non symmetric if you want. Unless I made a mistake somewhere else. Not for now, they're fine. Okay. Okay. This is pretty much the explosion of words out of 4 symbols. Okay. Any questions about this so far?
So the product of the expectations there with the conditional and the marginal, because the idea that is deriving where you're ending up with the marginal, does the conditional family distributions there.
Ta-da! You will have to know when the lights come back. What's happening? It's probably, I mean, if it was me, I would have sit on the switch. Tommy, are you stressed out about the lack of light? Did you do something, or it was you? I completely sympathize. I usually turn off computer that way. No, so there are minimal. The question is, can you always do this? There are minimal assumptions. Kind of almost usually yes. And there are like result. I think it's called Aumann principle. There are things that basically said that if you because there are more questions from an optimization, convex optimization point, or optimization variational point of view. Is always true that you can minimize this or minimize this pointwise and you get the same thing? No, it's not. You need some regularity assumption, but they're very mild and typically we're always going to hold for our setting. That's a fair
Going from here to the optimal function that is corresponding to a different choice of last function.
Let me give you the example. I skipped this because it's easy, but let me just give you an example in the case of square loss. Okay, for the square loss, you're gonna do 1 for classification. Okay, f of x, p of 1 given x. Then you have to do plus the other label, which is -1. Oh no, sorry, this is it. So it's -1. F of x square, and then I have to write p of -1 given x, but it's 1 minus p of 1 given x. Well, it doesn't matter actually, you can write it like this. Okay? I just wrote this inner risk, this inner part for the square loss for classification. But the point is that now you should consider this as a number, call it beta. It's just a number. So now take the derivative with respect to beta, set it equal to 0, and see what you get. You get this. Okay? What about logistic? Well, you do the same game. What if it's not regression? Well, you're not going to have a sum. You're going to have an integral just on the y's. Does it make sense? So I skip this because it might be also part of some of the exercises. But it's literally one. It's more conceptually interesting than mathematically interesting. You just take derivative of a one-dimensional function. Does that make sense? Was there other questions? Yeah.
So what in the case when it's not differential? I know there are some times where it's only mostly differential. What about that one with the indicator function?
So in those cases, in those cases, basically, I do it. I mean, the cases I know, you cannot do it by hand. Okay, indicator function, you really do it by hand. It's so simple. You just have 2 values. You look at them and you see that one is bigger, the other one is smaller, and the other way around. It's a little bit more interesting in the case of the hinge loss function. Okay, there is a little bit more structure, and again, essentially, you study, no, that's too fancy. This is more like high school stuff. I study the graph of a function in 1 dimension when it's not differentiable. Find the minimum. You go there. You divide it in pieces. You write this. You write that. You write that. And you see that it's kind of like this or kind of like that. And you're like, oh, okay. Okay. This is because we're not trying to make computational. It's not something we want to code up. If you want to do something that we want to code up, we're going to go to something like that. Or you can be fancy and do subgradient. It's the same thing. But in this case, I think the simple way, just think of this as high school math. Okay. You just look at the graph of the function and you see what's going on. It's not worth shooting at it with the subgradient. Anything else? Okay, so in the last few minutes, what we want to do is to spend a couple of words on actually somewhat sophisticated concept that we're just going to introduce briefly, just to give you some ideas. And a lot of these ideas are going to be again the start of the more statistical part that Sasha is going to teach in a month or so. So I'm just going to give you a couple of highlights. Okay, the first one is Okay, well, what does it mean to solve the learning problem? Well, to solve the learning problem, first of all, we have to find some procedure that, given this set of points, let me give it a name, okay? I'm gonna call S of n the sample, what is sometimes called the training set, the input-output pairs. And we're looking at a procedure that spits out a function. We're gonna typically use the notation hat to somewhat indicate things that depends on the data. Okay, we're going to drop the explicit depends on the sample S and even to the subscript N. We're just going to do the hat unless it's particularly confusing. If you get confused, remind me to explain this. But hat is like depends on data typically. Okay. So this is somewhat an abstract way to look at learning procedure. Okay, it's just any black boxy abstract thing that, given the data, returns a function. Okay, a function that will somewhat solve this problem. So, what is the way? What is a possible way? What is the natural way, given a candidate function f of it, to decide whether it solves the problem or not?
F hat minus the expectation allowed.
Say it again?
F hat minus the risk, the expectation.
I call it L. Okay, so I'm going to write minimum like this. Like this. Almost. We have to fix it, but that's roughly the good idea. We are trying to solve that problem. Now we want to try to see. Well, now I'm comparing, though, a function to a number, so that's not the good idea. What do we want to do? What do you want to do here? Well, if you minimize a function and you cannot do it exactly, you still want to see if you can do it. Okay, you want to know the value of the function here, how far it is from the value of the function that you are shooting for. Of course, you cannot do this in practice, but this is the natural way. If you want to minimize something and you do it approximately, you try to see how far you are from the exact minimum. Okay. Now, if you're a mathematician, you can also say, why don't I look at the function themselves? That would be the very natural thing to do from a mathematical point of view. Okay. And you can do that, but typically here the point is that this thing here has for us has a meaning. You know, L of f means the error on future data, which is what I really want to do. If I have two functions that are somewhat different, but they actually end up having the same exact effect on the data in my prediction, I don't care. Okay? So in some sense, this makes the problem easier. I don't want the function to be similar at every single point. I typically want the function to just produce the same performance on future data. So this is, let me rewrite it because I exceeded myself in writing this in a funny way. So this is for us as a meaning, okay? This is a fairly natural thing. If I define the problem that way, this is a fairly natural way to measure success. Of course, given an algorithm, trying to achieve this is going to be part of theory because pretty much every symbol I wrote, we don't have access to. Okay, machine learning algorithm is going to be about come up with a choice of f of it. Machine learning theory is going to be about proving that you can actually establish these kind of results. Okay. Well, what I wrote on the board doesn't really make sense from a mathematical point of view, even just from a conceptual point of view. Why? I mean, actually, what I wrote is fine. It's what I didn't write is the problem. Something is missing.
I mean, Fn is randomly samples that depends on the actual sample.
Right. What does that mean? I mean, f of n depends on the sample, on the data I have today. Okay, but it's just a sample, so I could have got a different set of data. So, what kind of guarantees I want for every data set I can possibly have? On average, do I want to control the distribution? So that's, in other words, that is not just a number. It's a random number. For any training set, you obtain a different number. So one natural thing is to actually consider the distribution. Okay. One is something like a cumulative distribution. You actually have this real number, and you try to understand the behavior of its distribution. Okay. That make sense? Notice that this is much more than just the average behavior. It means that I can, putting epsilon really big, I can go and see the tail behavior, the kind of worst case scenario. I look at the training set that are, I basically measure how many training sets that really look really, really bad. Okay, I allow myself to actually span the whole range of situations that could possibly happen. The things are related, okay? They're not, you can go from results in expectation rather than probability. I'm going to stick to this, and typically if you want to look a bit more into it, they're the same relationship you have between the different notion of convergence of random variables. Weak convergence, convergent expectation, convergence almost surely. Here we're just going to stick to this. What is the minimal kind of requirement you want to make on that quantity? So you would like to get something that is good, okay? That somewhat solve the problem on the left, and this is the way you measure success. You check how many training set give you a solution whose future performance is close to the best possible performance. This in words is what I wrote, okay? Well, there are at least two basic questions you can ask on that quantity. You want to know typically how it behaves, yeah?
Want to go to 0, want your function to approximate the actual target function.
Right, so one is, if my number of points increases, presumably I would want that quantity to actually go to 0, right? Hopefully, okay? What more? Is that it, or do you want some more? Well, in practice, you don't have any infinite data. So in some sense, knowing that as you get more and more data, you can get to the right place is kind of a sanity check. If you have an algorithm, the more data I give you, it goes in the wrong direction. It doesn't necessarily mean it's a bad algorithm, actually. It might have a transition. It might have for small samples, it works well, but if you go... But typically, most algorithms have this property as almost as a sanity check that they're okay. But again, you don't have infinite data, so what do you want typically? Well, typically what you would like to know is to know for a given amount of data how far you are from the solution. And saying how far you are in this setting requires a bit of care. So you would like to know, given endpoints, you would like to quantify this, okay? So the idea is that you would like, for example, to quantify this probability. You have an explicit bound on the probability, okay? You would like to know what is how, given n, you can achieve something like this. Of course, the more epsilon is small and delta is small, the more you expect n to become large. If I want to solve the problem very, very carefully, I will need more data. But if I want just a rough solution, then I might be able to do just not so many samples. So typically, the n that allows you to give something like that is going to depend on epsilon and delta. Okay? And here, p is fixed, f is fixed, and that's all I'm looking at. This is what is typically called it's been called in the literature the probably approximately correct way to solve a problem. So you cannot solve the problem exactly, so you want to solve it quite well in most of the situation. So this is quite well. Also, this is quite bad. Almost never, okay? If you prefer, you can swap the two inequality, and you will have that you want to solve it quite well. You want epsilon to be small, and you want to solve it quite well in most situations, okay? And the whole game is to try to quantify to which extent, this is going to depend on n. Okay. So again, what we're saying here is just we define the problem that way. Now we want to somewhat introduce what is the notion of solution, what is an algorithm, how we quantify those good an algorithm. And we're just saying a couple of things. The first one is one natural way to assess the quality of a solution is to see how far is the value of the function I want to minimize to the value of the problem that I wanted to look at. And then I have to just be a bit careful because this is a random quantity. And among all other choices, we're going to focus on this way of quantify the behavior of the random variable. We're going to study its cumulative distribution. And we might be interested both at the asymptotic behavior as n increases, but also at the finite sample behavior for any fixed n, and characterizing how the random variable behaves for varying threshold accuracies and confidence epsilon and delta. Was a question? Was it? Okay. Yeah.
Don't we need an absolute value of the loss differences?
This guy?
Yes. Can't L of f hat go below the minimum of L of f?
No.
Even if you have.
Because you see, so far I'm shooting pretty high. I'm shooting for the minimum along anything. And that's a pretty low value.
If you only have one point.
I mean, so this is always smaller than this, right? There's no way anything can be bigger than this. Then with probability, I see how they fluctuate around. This is the minimum, is a deterministic function, is the minimum, okay? So, and this is not the error on the data, it's the error on the true expectation. So it's like, I take a function, I take its minimum, and there's nothing below it. So, that makes sense? Okay. I think I probably would stop here. Yeah. So in the notes, if you look, there is a bit of discussion on how you build algorithm beyond this point, but we're going to basically introduce it in a more hands-on way next time.